All right. So, hi, everyone. Welcome once again to Metaflow Office Hours. Our first speakers for today are Mateusz Kwasniak and Simon Klimovics from Deepsense.ai. Mateusz is an MLOps tech lead at Deepsense. Deepsense.ai helps companies implement AI-powered solutions with main focus on AI guidance and AI implementation services. Previously, he's been an MLOps engineer at companies like Millennium and Hexagon AB. Simon has been with Deepsense.ai for the last 2.5 years and is a colleague of Mateusz. Gentlemen, over to you.
Thank you, Sri. Okay, so let me share my screen first, and then let me present you what we prepared for you today. All right, so the topic of our today's presentation is Metaflow on-premise. This is going to be the case study for the platform that we have developed internally at Deepsense.ai. So we are just going to present you the architecture and also some preview of our platform, and also we are going to mention the some challenges that we stumbled upon related to Metaflow itself, or the on-premise deployment, and also how we figured those out. So just like you already heard, it's me, Mateusz. I'm the lead MLOps engineer at Deepsense.ai, and here's also my colleague Szymon, who is a Python software engineer and is also a core contributor of the Deepsense.ai platform. And as for the company itself, so you can think of Deepsense.ai as a sort of software house, but AI specific. So we have right now over 100 experts, both data scientists, machine learning engineers, data engineers, or MLOps engineers like myself. And we work with different clients to provide them custom tailored AI services. So these are both the models or machine learning pipelines, or the whole platforms themselves. So we work in many areas, many areas of the machine learning lifecycle, and also various domains. And because of that, so because we tend to work with so many clients, and we have to train the models and do the analysis, sometimes on the client's infrastructure, but very often also on our internal hardware. We wanted to have the solution for that, so sort of internal ML platform that we could use at Deepsense.ai. And this is exactly going to be the topic of this discussion. So first of all, I'm going to just briefly describe how we actually started to think about the platform in the first place. And then we are going to delve deeper into the architecture and specific components of our Deepsense platform. And last but not least, we are going to step down, go a bit on a lower level, and describe specific issues or tricky puzzles that we had to solve. So let's move on to the platform itself. So the context here is that, as I mentioned, we've got many clients and projects for which we very often have to train our models for the client, process data, and implement machine learning pipelines. And we wanted to do that on our infrastructure. So first of all, when we started to think about developing the platform that we right now call the DS platform, we wanted to interview all of our stakeholders that we have at the company. I believe that this is the very first step that you should do anytime. So those stakeholders, so there are like two main stakeholders that we identified. First of all are obviously the direct users of the platform, being the data scientists and machine learning engineers. And as I already mentioned about Deepsense.ai, we cover many different domains and problems that you can meet in machine learning and in data science. So we had to make that platform quite generalized to that, right? And the IT team was also a very important stakeholder for us because it's a team that naturally controls all the hardware and whatnot, but also there were some specific requirements. For instance, we do own our internal hardware. So for our internal projects, we do not use any cloud provider. That's related to our scale. So actually, it's better for us to use our hardware at this point. And also because we tend to work with our clients' data, it's easier for us to guarantee that data is being private and safe on our internal infrastructure than it is while using cloud providers. So those were also some requirements that we had to take into account. And also based on our experience with building machine learning platforms for not only ourselves, but also our clients, we had to focus on some basic principles. So for instance, when you build the platform, you have to remember that you're not actually building some product that is tied to a specific business metric, but rather you should think of the platform as a building blocks that then will be used by product teams. And let's not forget in this slide, that's what I'm going to, is that you only would like to provide the building blocks that teams are actually going to use, right, to build the product. So this is why we did the interviews, and it took us a while to identify the real requirements so that we implement what's really useful for the teams. And the other thing that we took into account is to make it really simple to be used, especially because we already had some sort of a maybe not a platform itself, but a development environment. So to make people switch, we of course don't want to do it like by force, just shutting down the old development environment. We would like to rather convince people that it is actually something better, it's easier, and it can make your work better, right? So we had to think about that to make it work exactly for their needs and to make it as easy and as pleasant to make them switch naturally. And in the end, after all of those interviews, there are some core conclusions that we identified that then led us to our architecture. So first of all, the development environment that I mentioned was basically our hardware that you could SSH into, and there's a SLURM layer installed on every machine. So we had a way to experiment, but we had a problem with optimal orchestration of the jobs and whatnot. So on a high level, we decided that because we also have our hardware and machine available, maybe it is a good idea in long term to switch to Kubernetes, which is an interesting standard, not only in like typical software engineering, but more often in MLOps as well. And because of that, we could also improve our utilization of resources, like GPUs, for instance. So the idea was that we will no longer need to reserve the whole GPU for a specific person or a team for a day or a week, nobody knows. But we could utilize that better, and we could delegate that to Kubernetes to orchestrate that for us. And when I mentioned the blocks that we are building, we identified that most of the cases are like data analysis or just preparing the models themselves. So we very rarely go into the real deployment and like productions, because whatever we do on our infrastructure, it's usually just being handed over to a client, unless it is some internal application. So these are the use cases that are the most common. So because of that, we wanted to focus on something that lets us prototype our solutions quickly, and also for those a bit more complex solutions, we wanted to have a solution that could utilize, for instance, pipelines. And this is exactly the moment where we decided to use Metaflow. And also, Shimon is going to talk about that later. But as I mentioned, with our many clients and data privacy concerns, we had to make sure that whatever we produce is supporting multi-tenancy. So this was also our one of the main conclusions, right? All right, so having those conclusions in mind, let me actually show you what we made out of it. So just briefly recapping what I mentioned earlier, we wanted to improve the utilization and the allocation of our hardware resources and make them more scalable. We wanted to make this platform as easy to be used as we could. And also we wanted to sort of implement the standards for not only existing, but also future projects, so that we can make the switch easy for all the projects and make the adoption of our platform even easier. And that applies to those two pillars, which I also mentioned. So the quick prototyping, let's say, with notebooks. And we could argue for hours if notebooks are hot or not, but sometimes they are just very convenient, right? And if not, then we wanted to support some real mature workflow orchestration tool like Metaflow. And in the end, so what we have in our platform is the Metaflow, which is also backed by the Argo workflows engine in the end. And for the prototyping side, we have Jupyter Hub that is also deployed within our cluster. So those are the user-facing services, and also there is a group of services specific to the management and administration of our platform that I'm going to mention in the next slide. And also about the per project separation, there's this the thing that we are going to discuss in details later. But this was also a thing that dictated many of our architectural choices and caused us some issues, but we got through that. So going to the diagrams, to the pictures, let me just quickly describe what's here. So as I mentioned, we've got the user-facing services, as we call them. So this is Metaflow and Jupyter Hub. And also for that, we use Min.io as a object storage. It's also going to be useful if we decide to switch to cloud at some point. So this was also why we decide to use it as a natural choice. And then on the not the user facing, but the what I call the administrative side of the platform, there is Argo CD to manage our deployments, which we use with our platform repository containing different Helm charts. And the GitOps deployment pattern. We also use Vault to keep our secrets, along with the secrets operator, and also a bunch of authentication services like DEX that is also connected with our Active Directory, so that we have the authentication layer the same as we do for any other internal services that we use at the company, and in the end to make the switch even easier. Yeah, so this is what I described just before. Yeah, is there any
Quick question here. So yeah, quick question. Is that okay, or do you want to take it at the end?
Go on.
So if this is all in one Kubernetes cluster, like all these components that you are talking about, they're all in one Kubernetes cluster?
Yeah, so there's one cluster. We are going to replicate that to make also, or we actually have test cluster already, if I'm not
Got it.
wrong. But yeah, like apart from this staging and production cluster, it's also it's all in one. The only issue that we had with multi-tenancy, so let me actually start this topic earlier, is that we were not able to separate all of the issues. So the issue here is that if you can imagine a company like a Deepsense.ai working for many different clients, and you are assigned to a specific client or a project, then you should only have an access to that specific client's data, and you should,
Right.
the enemies don't have access to any other. And also, like, not only data itself that we store on our NFS volumes, but it also applies for the scripts and notebooks and so on. So in the end, what we ended up with is having the same cluster, but having that separated on a namespace level. So we have a separate deployment of Metaflow for each client, and we also through Airbag grant the access separately to our users per client with the Active Directory groups, and this way we keep our data separated between projects and also accesses.
Got it. Cool.
All right. All right. So just a quick tour. We didn't want to risk a live demo here, but there are just a couple of screenshots that we prepared for you. So because the thing that I described just before, we decided to have this separation on a per project on a namespace level. But sometimes it is the case that you might be assigned to multiple projects. And we wanted to also make this use case easy for our engineers. So we built a very simple dashboard. We are Deepsense.ai, not a front-end company. Although we have great front-end engineers, but this is not the thing that we wanted to focus on. So we have this very simple dashboard that is a sort of entry point to our platform, and in which you can just sign in, and there's a list of projects that you have an access to, and for each project in the list, you have the Jupyter and the Metaflow UI, with, of course, a possibility to extend that to other services in future. And then if you choose to use either Jupyter or Metaflow, yeah, this is the authentication screen. We used Dex for that, which has a nice integration with LDAP. And yeah, Jupyter Hub is what it is, just for a quick prototyping. I guess that's what we already are familiar with. And there's also Metaflow, which is, so right now I think it's most of the cases anyway. So Jupyter is there for some quick experimentation, but whenever projects use our platform, they use Metaflow, even if these are just simple ones that flows, they still tend to use Metaflow. Maybe that's because we also provided some project template based on cookie cutter, and then we provided a simple pipeline for them to make the integration easier. So we are kind of pushing them into the direction of having the reusable and tested pipelines rather than just notebooks. But yeah, so this is the fact, and we are happy about it. That Metaflow is being utilized within our platform. Yeah, you already know the UI, so I'm not going to delve any deeper into that. We are going to to look at the details right away. So now, Shimon, the floor is yours.
We are not able to hear you, Shimon. Not yet. You were able to at the start of the call.
So in the meantime, are there any questions to the part that I described so far?
One question about the notebooks versus or notebooks, use of notebooks. So do people write code, like do they write Metaflow flows in the notebook and then run it in the notebook, or then sometimes just like if you add that Kubernetes decorator or whatnot, like then run it on the backend?
Yeah. So what we advised is to use the Kubernetes decorator.
Yeah.
So and then this is also the flow that we've been testing and recommending and pitching to our users to make the switch between your local execution and remote execution with ease. We also had to make few improvements there. So for instance, the thing that I think was not available back then at Metaflow is the automatic tagging of the executions, whether they are executed locally or remotely. So we wanted to have that automated. So looking at the Metaflow UI, we know exactly which one was executed remotely and which one was locally. And also the other thing was that we wanted to know exactly which user executed a certain execution, and that was easier for the local deployment, local execution. But we also managed to get those details from the our kubectl and to also get the identity of the caller for our remote execution, so that we have a clear history for all the remote runs.
Okay, sounds good.
Okay, I hope you can hear me now.
Yes, we can.
Okay, fantastic. Thanks for the patience. So let me share my screen real quick. Can you see the presentation?
Yes.
Okay, so hello. I'll be presenting some of the greater challenges that we faced when integrating Metaflow into our platform and how we solve those challenges. So first, some of the issues and features from the service perspective. The first is port forwarding from local environment to Metaflow backend and MIO services. So on bare metal Kubernetes, we had to allow for user communication to these services, but we did not want them to be quote unquote public, so to say, like the UI service. So we resorted to allowing users from a given project namespace to port forward to these services when running the flows. This was implemented in our fork of Metaflow, and is happening automatically in the background during every execution that is done on the cluster, so that it's called remotely.
Oh, nice.
The next issue, or feature rather, is adding a debug step decorator for debugging remote flows with WebPDB. This is one of the most requested features on the platform when using Metaflow. We enabled debugging of Metaflow flows with the help of this package, WebPDB, and again, port forwarding to the cluster to allow users to connect to a debugging session running on the same pod that the flow is executing on. A user just has to mark a step as a debug step with the decorator and use the Python standard library breakpoint function. This opens up a service on the pod that is port forwarded, and the link to access it is shown in the flow logs. The debugger is simple, but it's more than capable of serving our needs for testing and sanity checks.
Nice.
The next thing is aligning Metaflow with our standard repository structure. So for like 90% of our projects, we're using a standardized cookie cutter repo template. We really wanted to integrate this template with the platform to allow for seamless work with Metaflow. So we had to change a little bit how the code is sent to the job pod. And by default, as you know, the flow script has to be at the top level directory in order to recognize and copy the code to the job. But we wanted to structure that differently, as we have in our repo template, as shown also on the presentation, as we feel like that the flow script should not be really a part of the base code package, as this is just one of the many interfaces that the code package can be used. So we kind of changed the behavior to copy the whole repository from its Git root. So it's, I suppose it's kind of Git cloning the repository to the pod. And then we leverage the git ignore mechanism for easier control of what files should be included or excluded from the job. Another feature we added was adding a pip decorator for installing both remote and local packages. Pip is our preferred way of managing packages, so we naturally want to have that in the flows. Of course, during the time we're implementing the decorator, this feature wasn't available in the base Metaflow package. I know this is the case now, but the main takeaway is that the decorator had to allow for installing local packages available in the current project directory. This was very important to us. Yeah, and next I'll touch on some issues regarding the infrastructure deployment and multi-tenancy. So the first issue was per project deployment for data and sensitive information protection. And from Kubernetes side, like Mateusz said, we used namespaces to separate the projects and role-based access control to enable users to access selected project resources and, of course, deny them access to any project resources they're not a part of. And that, of course, includes all the Metaflow services, backend and UI, Jupyter notebooks, or any other resource that is user-facing. For data access, we use NFS, and we also use FreeIPA for user and group control. So the access to the NFS data is managed by the group membership of users. So naturally, users can only access NFS resources that are available either directly to them, to their user ID, or to the group they're a part of. This all was used in pair with mounting the project NFS data to the job pods to allow the flows to work on the data with proper access.
Nice.
The next issue was authentication for each services deployment, and we managed to solve that with PowerOf2 proxy and DEX. The configuration of the proxy for each deployment was managed through the ingress resource of that deployment in configuration there. That enables external access to the UI service in the cluster. So the proxy intercepts the traffic to the UI and gets allowed group configuration from the ingress resource, and then verifies the group membership of the user with the DEX service. So if the user is part of any group that was listed in the configuration, they can, of course, then access the resource. And the last point here is managing pod security context through mutating admission controller. I know this sounds a little bit cryptic, so let me explain here. We had some issues with how to integrate with the FreeIPA user and group IDs to allow Metaflow jobs access to the NFS data as the user that executed the flow. And we had to do all that without the user being able to tamper with the IDs in the manifest that they were deploying to the cluster and sending to the Kubernetes API. So during testing, we actually find out that it's pretty easy to impersonate other user from the project group. This wasn't any major risk, as the data that was mounted to the job pod was only for this given project. The access to services was limited by the Kubernetes namespace and airbag. and all the users also basically have the same permissions. Still, we wanted to take care of this challenge, so we used the mutating admission controller to intercept the manifest heading to the cluster and patch the pod security context using the mutating admission webhook mechanism. This webhook is a custom microservice that after the request is authenticated and authorized, as you can see on the diagram, it reads the user information passed in the manifest, gets the user IDs from our free IPA or LDAP service, and then returns the patched version of the manifest containing the correct user ID and a more tight security configuration. So this allows the job pods to act as the user that started the job with all the correct NFS data access. This manifest is then passed further to create the resource as normal. Okay, and that's it from our side. Thank you. If there are any questions, we'll be happy to answer them now.